Hi, and welcome back. The present module, which also happens to be the seventh module of the short-term course on computational chemistry, and it is about geometry optimization and frequency calculation. Now, using frequency calculation, not only we get the IR spectrum of the desired molecule, but it is also useful in identifying the nature of the stationary point on the potential energy surface. Additionally, we get information about zero point vibration energy and thermal correction to the total energy, and hence we can get some important thermodynamic quantities like enthalpy, entropy, and free energy, and also we can do some useful thermochemistry. Taking acetone as an example, let's do a combined geometry optimization plus frequency calculation. So from the element drop-down menu, choose carbon. It's already in the selected mode. Click on the display panel. Click and drag once more. Now you have propane. Now let's convert the central carbon atom into a carbonyl group. So from the element drop-down menu, choose oxygen. Click on this carbon and drag to get a carbon-oxygen single bond. Now click at the center of the CO bond to convert that to double bond. Done. So before moving forward, first let's clean up this molecule using molecular mechanics force field. Go to auto optimization tool. Choose the desired force field. Since it's an organic molecule, so we'll go for Merck molecular force field. Click on the start button, and very soon we'll get optimized geometry but at molecular mechanics level. So wait for a while. Done. D equal to 0. So do remember to click on the stop button. Now let's try to create input file for a combined geometry optimization plus frequency calculation. Go to the extension menu. In the ORCA option, click on the generate ORCA input. Give a proper comment. So let's write OPT plus frequency of acetone. And then in the calculation drop-down menu, choose geometry optimization option. So you can see that in the line which starts with exclamation, this is the line for the important keywords. You get important keyword OPT. OPT stands for optimization. Since we want a combined job for optimization as well as frequency, go back to the calculation drop-down menu. Click on the frequency. So you get an additional keyword for the frequency calculation. Now let's convert this basis set into Popel split basis set, and that is, let's write 6 3 1 1, then diffuse function, and then also a polarized function. Now in the present module, in the theory section, I think in the first lecture there is a complete description on the basis set. So my advice at this moment is, first go to that particular theory lecture and then have a proper understanding of what does this mean, and then come back to this particular lab session. So let's click on the generate. Save this input file with a proper name in your desired directory. Let's name this as acetone. Click on the save button. Let's close this window. Let's minimize this. Then open the command line using the run option, and then navigate to the desired directory. So cd, that is in my OneDrive, /desktop. I've created a test directory. Within that, I have another directory with the name acetone. And let's check that if I have got my input file there or not. Yes, there. acetone.inp. Now let's run an ORCA job. So the command is ORCA space name of the input file, then space channel 2 space, give a name to the output file, Change the extension to out and click. So done. Now let's try to analyze the output file. Let's minimize this. Go to the desired folder. Then open the folder which contains all the output files. Now let's open file with the extension name .out in Notepad++. And now if I scroll downward, you'll see information regarding the basis set which we used for this particular job. This split basis set came from the group of John Pople. John Pople got the Nobel Prize, 1998 Nobel Prize for Computational Chemistry. And that's the description of the original paper. Go downward. That's a summary of the input file. So in this case, we did a combined job of optimization and frequency using restricted Hartree-Fock method with this particular basis set. The description about the geometry of the molecule was provided in terms of Cartesian coordinate. But you see that they'll do the geometry optimization using redundant internal coordinates. That's the line written here. The optimization will be done in a new redundant internal coordinates because internal coordinates contain information in terms of bond length, bond angle, and dihedral angle. That means they provide information about the connectivity in the molecule. So this is helpful, and the geometry optimization is bit fast. But this will be helpful only when you have a single molecule. But if you have a collection of discrete molecules, then there might be some issue in the geometry optimization if you use internal coordinate. So in that case, what I'll suggest, start reading the ORCA manual. So that's the ORCA manual. If you scroll downward, that's the contents available in the manual. The most important section in this case is section 8. That's running typical calculation. Within that, in the section 8.2, there's complete information regarding geometry optimization. You'll find discussion on coordinate systems for optimizations. So you'll see that that's the right line written there. The coordinate system for the optimization can be done by the coordinate system. That's the word they use for coordinate system variable, which you have to provide in the percentage geometry block. But normally this is done when the optimization fails with the redundant coordinate. So if there is a problem in optimization using internal coordinate system, then you can switch over to the Cartesian coordinate using this particular word, writing this particular word with Cartesian in the percentage geometry block. But when you use Cartesian coordinate for geometry optimization, it will be a bit slower, only slightly slower than what we have for the default redundant internal coordinate. Okay, so let's make it a practice to refer to the ORCA manual for the complete description. Go back to the output file. Let's scroll downward. Now the very important one. So let's have a tutorial on this particular section, because in the present module, in the first lecture, there is a complete description on the basis set. So let's try to understand all the terminology and the value which we got in this particular case. How come we got the total primitive Gaussian function equal to 194 and the total contracted basis function 130? And what are these terminology stands for? So in acetone, how many atoms you have? The molecular formula of acetone is CH3, CO, CH3. So 3 carbon atoms, 1 oxygen atom, and 6 hydrogen atoms. The total 10 atoms. The basis set which we used in this case is 6. Let's make it a different color. 6, 3, 1, 1. That's the split basis set. What does that mean? We are using 6 Gaussian function to create a contracted Gaussian function that is called basis set. Contracted basis function is created by the help of 6 Gaussian functions for core shell orbitals. Whereas for valence shell orbitals, we use triple zeta. One set of valence shell orbital will be made up of 3 Gaussian functions each. Another set will be made up of 1 Gaussian function, and the third set will be made up of 1 Gaussian function. We'll understand this. And then we provide a diffuse function. If you have only one plus, that means you are providing diffuse function for period 2 element, that is carbon and oxygen. And if you provide another plus, it means you are providing diffuse function for hydrogen also. And then if you write D in the bracket, it means you are providing a polarization function for period 2 elements, because with the help of this 6311 and plus plus, you can only modify the size of the orbital. But if you want to modify the shape of the orbital, you require polarization function. So you provide an orbital, with higher angular momentum. So in case of carbon and oxygen, the only orbitals which are used for writing the ground state configuration is S and P. But you are also providing D type orbital for carbon and oxygen. So remember, more the number of functions, more the number of basis function, better the calculation is, more accurate the calculation is. If you want more accuracy, you can also go for providing a p-type function for hydrogen. So for hydrogen, the configuration is 1s, but you are also providing p-type function in order to allow them to change the shape. So that's the basis set which we use for this particular calculation. And let's see how, using this particular basis set for acetone, we got these numbers. So for carbon, the configuration is 1s2, 2s2, and 2p2. So the orbitals which are used in writing the ground state configuration for carbon and oxygen, 1s for the core electrons, and 2s and these 2p's for the valence electrons. So 1s is the core shell orbital, and 2s, 2px, 2py, and 2pz are valence shell orbitals. Now, for the core shell, that is for 1s is made up of 3 Gaussian functions. Sorry, 1s is made up of 6 Gaussian functions. That's the 6 there. So this is for the core shell orbital. So 1s is made up of 6 Gaussian functions. So let me write this as GF Gaussian functions. From now onward, I'll use this for writing Gaussian functions here. Now, the valence shell orbitals, for that, we are using 3 different sizes, that is triple zeta. So 3 different set of contracted basis functions for valence type orbitals. So for 2s, 2px, 2py, and 2pz, that is one set of valence orbitals. We are making each valence set orbital by the help of this three Gaussian functions each. So each 2s will be made up of 3 Gaussian functions. Each contracted basis function 2s will be made up of 3 Gaussian functions. Each 2px contracted basis function will be made up of 3 Gaussian functions. Then another set of valence shell orbitals, that is, let this be prime 2s prime, 2px prime, 2py prime, and 2pz prime. And that's, each one is made up of 1. That's the meaning of 1 Gaussian function each. Then the third set, 2s double prime. So more the number of basis set, more the flexibility in the size. So one Gaussian function is, that's the third one, this one. So the first set of valence orbital is made up of 3 Gaussian functions each valence orbital. Second set is made up of 1. Third set is made up of 1. Now, if the system has atom with negative charge or lone pair, then in that case you are required to provide function which can spread up in bigger space. So for that you provide this diffuse function plus. Plus means you are providing another set of valence shell orbital but with a bigger size. For carbon, second cell you can go for the third cell type. So you'll have another set of function which will mimic things like 3s, 3px, 3py, and 3pz. So that's the meaning of this 1 plus. You're providing orbitals with a bigger size, but each one is made up of one Gaussian function. And now the fourth one, that is you're providing a polarization function, one set of polarization function for carbon and oxygen in order to permit them to make a particular change in their shape. So you provide an orbital with higher angular momentum, so that is 3D. Now you'll see the sign XX, YY, ZZ, and then 3D XY, 3D YZ, 3D ZX. The reason is, if you remember, Gaussian type orbital, general way to write that is x to power a, y to power b, z to power c, e to power minus zeta r square. R square is x square plus y square plus z square. So a d orbital can be obtained when the sum of a plus b plus c is equal to 2. So that can be, one way is 2, 0, 0. So 2, 0, 0 means xx. In x you have 2. 0, 2, 0 is yy. If you make it 1, 1, 0, then it is xy like that. But in that case, you get a 6 combination. But this 6 combination will be equivalent to the 5 3Ds. The typical one, that is xy, yz, zx, x square minus y square, and z square. So this will be counted as 5 knot sets. And for each, we have one Gaussian function. That's a complete set of basis functions and the set of contracted basis functions for carbon and oxygen. Let's count them. How many total? Now, what does this mean? This 12s, 6p, and 1d. That's written here, 12s, 6p, and 1d. So if you add this, how many s there? For s, how many Gaussian functions used there? 6 for 1s, 3 for this 2s, 1 for this 2s dash, 1 for this 2s double dash, 1 for this 3s. So for s, it will be 6 plus 3, 9, plus 1, 10, that plus 1, 11, plus 1, 12. So that is 12. So let me make this with different sign, different color. So that is, we are using 12s. For p, how many Gaussian function? Add this. 3 for each 2p, 1 for this particular 2p dash, 1 for this 2p double dash, 1 for this 3p. So 3 plus 1 plus 1 plus 1. Total it will be 6p's. 6p Gaussian function, that's the meaning of 6p. And 1 for each d, that is 1d. That's the terminology for this. Contracted to how many contracted basis function? How many type of contracted basis function for s? It will be 1 for 1s, then 2s, then 2s dash, 2s double dash, and 3s. Total s will be 5 types. It will be 5s. So this is 5s. And then how many p? That will be 2px, 2px dash, 2px double dash, and 3px for each p. So total 4p. And how many d? Each one is 1d. That's this terminology. 5s, 4p, and 1d. So this many functions, Gaussian functions, contracted to this many basis functions. The pattern is, look at that. This is 6, 3, 1, 1, 1 for s. So this you can write as 6, 3, 1, 1, 1 for s. Then oblique, for p it is P, it is 3, 1 for each P. It is 3, 1, 1, 1 for this P. So this is 3 px, you can say 2px, 2px dash, 2px double dash, and 3px. So that is for 3p, you're writing 3. You're using how many Gaussian function? 3, 1, 1, 1. And for D, it is only 1. So that is 6, 3, 1, 1, 1 for carbon, 3, 1, 1, 1 for each 2p, and for each D, it is 1. So that's this meaning. This is the same for carbon and for oxygen. So let's count it. Total, how many Gaussian function? So total Gaussian function for each carbon and for each oxygen will be 6 in this case, 3 for each one. So 3 into 4. So that will be 6 plus 3 into 4 for one set, then plus 1 for each. So 1 into 4 plus 1 into 4 plus again 1 into 4 and plus this will be 5 into 1, that 1 into 5. So if you count that, it will be 6 plus 12 plus 4 plus 4 plus 4. So that is 12 plus 12, 24 plus 6, 30 plus 5, 35. So we have 35 Gaussian functions per carbon atom and per oxygen atom. How many total contracted functions, total basis function for each carbon and oxygen atoms? That would be 1, 4. That is a contracted basis function. 1 plus 4 plus 4 plus 4 plus 4 and plus 5. So it is 1 plus 4 plus 4 with this prime plus 4 with double prime plus 4 for the diffuse function and plus 5 for the polarization function. So 4 into 4, 16 plus 5, 21 plus 1, 22. So 22 basis functions per atom of carbon and per atom of oxygen. Let's go for the hydrogen. For hydrogen, the configuration is there is no core electrons, only valence electron. So using only valence orbital, but that valence orbital is triple G. So one contracted basis function, that is 1s, which is made up of 3 Gaussian functions. Another contracted basis function that is made up of 1 Gaussian function. Another contracted Gaussian function double prime, again made up of 1 Gaussian function. That's the meaning of 3, 1, 1. You are also providing a diffuse function. That is, you're providing S but with a bigger size, that will be a 2s, but that is made up of 1 Gaussian function. But you're also providing P set, that is 2px, 2py, and 2pz, orbitals with higher angular momentum, and each made up of 1 Gaussian function. So how many Gaussian functions for each hydrogen atom? Let's first see the terminology. So how many types of S? 3, this, how many Gaussian function? So 3 for this 1s, 1 for this 1s dash, 1 for this 1s double dash, 1 for this 2s. So that is 3, 1, 1, 1. Total 3 plus 3, that is total 6s. So 6 type of S Gaussian functions. How many P types of Gaussian function? Each Gaussian function for P is, for 2px it is 1. So that is 1p. So that's the meaning of the 6s and 1p. So total Gaussian function used for S is 6. Total Gaussian function used for each 2p is 1. Contracted to how many type of contracted S-type orbitals? So that is 1s, 1s double dash, 1s double dash, 1s, 1s dash, 1s double dash, and 2s, so that is 4s. And each p, that is 1p. Clear? four type of s orbitals and one type of each p orbital. And then the way to the one to represent the Gaussian function terminology will be this S is made up of 3, 1, 1, 1. So this is 3, 1, 1, 1 for S. And for P, it is simply 1. So that's this 3, 1, 1, and 1. Now let's count total number of Gaussian function and total number of basis function for each hydrogen atom. So total basis function will be 3 for this 1s, 1 for this 1s, 1 for this 1s, and 1 for this 2s. So 3 plus 1 plus 1 plus 1, total 7, and 1 for each. Sorry, 3 plus 1 plus 1 plus 1, total 6, and 1 for each, total 9 Gaussian functions. So this is 9 Gaussian function for each hydrogen atom. And how many basis set? How many contracted basis function? So 4 this and 3 this. So total 7 basis functions for each hydrogen atom. This is for each hydrogen atom. Now the molecule has 3 carbon atoms, 1 oxygen atom, and 6 hydrogen atoms. So for 3 carbon, total Gaussian function will be 35 into 3. For 1 oxygen atom, it will be 35 into 1. So total it will be how much? 35 into 4, that is 140. 140 total Gaussian functions for carbon and oxygen. And for each hydrogen it is 9. The total 6 hydrogens, so 9 into 1. So 9 into 6. That's 9 into 6. 6 hydrogen. 9 for each hydrogen atom. So for each hydrogen atom, there's a 9 Gaussian function. There are 6 hydrogen atoms. So it is 9 into 6. So total, this is 35 into 4 is 140. And 9 into 6 is 54. Count this. This will be 194. So that's matched with this 194 Gaussian functions. How many contracted Gaussian function? 22. 22 for each carbon and oxygen. So 22 into 4 for carbon and oxygen. That will be 88. Plus for each hydrogen it is 7. 7 into 6, 42. So 88 plus 42, total it will be 130. So that's the complete tutorial on how using a split basis set, a more descriptive one having both diffuse function and polarization function, a triple zeta one for acetone, how the calculation comes out to have these values there. So hope you understood this. Now there's an assignment. Choose molecule of your choice and then use the same basis set, or you can also use a smaller basis set, for example, double zeta 631 with 1 plus and only a polarization function for period 2 element. So you can go for choices like you can use this 631 plus GD. Note in some of the books you'll find another way to write this. They write in this form 631 GD with 1 star. 1 star means 1 plus. So this will be written as 6311 G double star. Double star is for 2 plus there. So that's another way to write the same thing. So use this particular one. Take another example. You can take acetone also and see how many Gaussian functions and how many contracted basis functions you are getting in your case. So this is for this particular lecture. We'll analyze other part of this particular output file in our next lecture.